Assalamu alaikum. This is our sixth lecture of Advanced Electromagnetic Field and Waves. Okay, so in this lecture, first of all, in the starting, we discuss some problems that will help you to solve your problems related to those lectures we already did in our previous videos. Okay, so today's we will do some practical problems to know how you can solve your problems. Okay, so our first problem is basically the electric field relation is given. Okay, you can see here E, which is equals to E naught y cap cos of kx minus omega t. This is the equation, wave equation of in term of electric field. Okay, you have to find B. So how you can find the magnetic field when you have a relation of electric field? You already know there is a formula which we already derived, that you know that B is basically equals to n cap into E divided by C. So this is how you can find the relation. Okay, you can see the direction of electric field is in the y direction, because you know this y direction with E naught basically specifies the direction of the electric field. Okay, and this with your this x basically defines the direction of your wave. Okay, your wave vector, which is k. So x is in k and electric field is in y direction, so must be in the z direction, because you already know that always your x your you can say your electric field, your magnetic field, and your wave vector are always perpendicular to each other. If your wave vector is in x and your electric field in y, so B must be into the z direction. So how you can write the equation? Basically, the equation for the magnetic field now becomes basically, first of all, z direction, then you can see the relation of E. Okay, E relation is already given, you can write it as similar. Okay, E naught. Okay, and this is same cos of kx minus omega t. Okay, and divided by C. So this is basically the equation of magnetic field. So this is how you can find the relation of magnetic field when electric field equation is given. Okay. Now there is another problem for you, problem number 2, in which the given conditions are E naught is equals to 10 volt per meter, whereas B naught is equals to 0.3 micro Tesla. Okay, and what you have to find? You have to find Z naught. You already know the relationship between when there is Z naught, B, and E. So the relation we already derived in our previous lecture is, the relation is that H naught is basically equals to E naught divided by Z naught. Okay, so you also know that the given condition is this: B naught equals to 0.3 mu Tesla, and you know that B naught is basically equals to mu naught H naught, and then is equal to 0.3 micro Tesla. We need the value of H naught, so because we have to put here to find Z naught, so H naught becomes equals to 0.3 micro Tesla divided by mu naught. Now move Z naught upside, because we have to find Z naught. It becomes E naught divided by H naught. Now you have to put the value of H naught here. Okay, so Z naught becomes equals to E naught divided by H naught. The value is 0.3 micro Tesla divided by mu naught, comes upside mu naught. So after putting the value of these, you know that E naught is basically equals to 100, and your mu naught value, you already know it's a constant, which is equals to 4 pi into 10 raised to power minus 7. Okay, divided by 0.3 into micro value 10 raised to power minus 6. Okay, after solving you will get your answer, and your final answer is basically z naught is equals to 418. Okay, this is the value. How you can find the value of z naught, which is basically the impedance if e naught and b naught is given. Okay, so now let's move on towards the third problem. Now this is your third problem, and your third problem says that your wave vector, which is equals to k equals to 10 power 7 radian per meter, whereas your omega value is a basically, which you know that which is the angular frequency. The value of omega is 3 multiplied 10 raised to power 15. What you have to do, you have to find the phase velocity. So to find the phase velocity, we know that it is basically denoted by Vp. Okay, and we know the formula for the phase velocity is basically equals to omega over k. You just have to put the value of omega, which you already know, 3 multiplies by 10 raised to power 15 divided by the value of k, which is 10 raised to power 7. After substituting, you will get your answer, and the answer is basically 3 multiplies by 10 raised to power 8. And because this is velocity, so the unit is meter per second. So this is the value of the phase velocity, how you can find by this relation Vp equals to omega over k. So this is our third problem. So now let's move towards the fourth problem. Our fourth problem, but the statement is simple, that your wavelength is given, which is now 500 nanometers. What you have to do, you have to just find the value of the wave vector k. Okay, uh, for this, to find the value of k, you must know about the relation of k and lambda, which is basically k, which is equals to 2 pi over lambda. Okay, so after putting the value 3 pi value 3.142 divided by lambda's value, you know that 500 nano, and you know nano is basically 10 raised to power minus 9. So after substituting, you will get your final answer, which is equal to 12.56 into multiplies by 10 raised to power 6 per meter. Okay, so this is the answer, how you can find the wave vector value k when your lambda is given. Okay, so this is your fourth problem. Now let's move towards the fifth problem. Our fifth problem is also very easy. Now your phase velocity is given, means Vp equals to 1.5 into 10 raised to power 8 meter per second, is passing to a medium. You have to find the reflective index of the medium. Okay, so you know reflective index basically denoted by symbol small n. You have to find this reflective index, and you know the relationship of the reflective index. We already tried this in our previous lecture. Okay, you can watch through watching that video. Okay, so the formula for the reflective index in some medium is basically equals to c by v, whereas c is basically the speed of light, and its value is 3 multiplies by 10 raised to power 8, whereas v is basically the velocity. In given condition, our phase velocity is given, and that was 1.5 into 10 raised to power 8. So after substituting, you will get your final answer, and your answer is basically 2. Okay, so this is how you can find the reflective index if the velocity in some medium is given. Our sixth problem is basically, now the relative permittivity is given in some medium. You know that basically relative permittivity is basically the electric response of some medium. Okay, so the relative permittivity of some medium is basically equals to 4 in non-magnetic medium. So this very crucial statement, this is in non-magnetic medium. Okay, must have to figure this out. What you have to do, you have to find the reflective index. How you can find, you know a relation. First of all, you already know that the reflective index is denoted by n, and you know a relation of n, basically it's equals to under root mu r epsilon r, where epsilon r is basically the relative permittivity, whereas mu r is basically the relative permeability. This is the magnetic response, this is the electric response. While in our problem relative permittivity 4 is given, but how we can find this mu r value? Basically we can find by this statement, in the statement written as it's basically non-magnetic medium. So for non-magnetic mediums, for non-magnetic materials, your mu r relative permeability is always equals to 1. Okay, we already show you this in our previous lecture. Okay, so in non-magnetic medium materials, so your mu r relative permeability equals to 1, whereas your mu r already given 4. So under root of 4 becomes 2. So your value is basically 2. So you can conclude a relationship between that if your relative permittivity is 4, so the reflective index is always the half, you can see, and basically equals to 2. So if your relative permittivity is 10, then your reflective index should be half. Means how, what is the half of let's suppose if your relative permittivity is 10, so the reflective index should be, okay, 5, half of that. Okay, so you can find the relationship. So this is how you can find the reflective index if either a permittivity of relative permittivity or a relative permeability is given. Okay, so this is how you can find. So this is our sixth problem. Okay, now we have to discuss some features like your epsilon r, basically the relative permittivity, relative permittivity is basically the function of position. You can write it at here x. Okay, and this relative permittivity is basically inhomogeneous. Okay, okay, this relative permittivity is basically the positions functions, and these are basically the inhomogeneous. Okay, so you can also say that you're either epsilon r or mu r, basically they are, you can say that, field direction dependent. Okay, field direction must be dependent in this case. You can see in our previous there must be some direction of that field, either for magnetic field or either for electric field. So these both are field dependence. Okay, field direction dependence. Without direction it's useless. Okay, there is another two forms. Your first form is basically an anisotropic, and your second form is basically isotropic. Okay, an isotropic medium and isotropic medium. And what's basically an isotropic medium? Anisotropic mediums are basically the mediums that are direction dependent. Okay, so you can say that your either epsilon r or mu are relative permittivity or a relative permeability. Okay, these both are basically anisotropic mediums because they both are basically the direction dependence. So what are isotropic mediums? Yes, you are right, it's basically direction independent. You can write it here, direction independent. Okay, so anisotropic are basically those are direction dependents, like your epsilon are relative permittivity or relative permeability mu r. Those both are anisotropic mediums, direction dependents. Okay, So there are some mediums that are not direction dependent, they are independent of direction, and those are basically the anisotropic mediums. Okay, another concept is basically in the case of like epsilon r and mu r. Okay, these must be scalar, but when both the directions are same, like this is an equation, the electric field basically equals to summation or E. If both the directions are same, then we can conclude that these are basically scalar quantities. Okay, similarly, like you can write it here for magnetic field relation, B is basically equals to, okay, mu and h. So if the direction for h and b and like e and d are same directions, then they are scalars. Okay, but what if both the directions are not same? Okay, if both of them's directions not same, either for the case of electric field and either for the case of magnetic field, if both the directions are not same, okay, not similar, then they are so called as tensors. Okay, tensors is a new relation in which both of them's directions are not same, so this is also known as called as tensors. So how you can write the matrix form of tensors? Let me show you here. Okay, and you can see here. Let's suppose in the case of electric field, as you know, D basically equals to some electric response epsilon and E, which is the electric field. Okay, so in the case of tensors, right here tensor. Okay, when tensors, when both of them's directions are not similar. Okay, so in that case your D's matrix your basically equals to your, you can write it as is here, exx, exy, exz. Okay, similarly eyx, eyy, eyz, similarly ezx, ezy, and ezz. So this is basically you can see all directions are not similar, exx, exy, exz. Okay, you can see. So this is basically how you can describe matrix form of tensors. Let's move towards our last topic of this lecture, number 6, and that topic is very important. And what's basically the topic is basically, suppose there is a medium and let's suppose an electric field is coming, you can say that it's basically E1, and your electric field is going out, basically E2. You must have to show with an arrowhead because this is vectors. Okay, so one, this is your first medium, you can write it here first medium, and this is your second medium, electric field is coming, striking and going outside. Okay, what you have to do basically, you have to find basically the electric field relation. Okay, electric field relation either for Faraday's law. Okay, you already know basically what's basically the Faraday's laws relation is. The Faraday's law relation is, you know, that is E dot dl, it's basically equals to surface integral partial b over partial t, okay, dot dA. This is for the other case, but in that case what we have to do, we have to do whole integral over d dot dl. Okay, it must be equals to 0. How, so how we can do this? First of all, we have to draw a loop here for this case. Okay, for this small box, let's suppose this is dl, and again this is dl. You can say that this is basically the dh, and this is also the dh downside. Okay, downside. So to resolve this, you first have to make the components of this. Okay, and this I draw, and this is basically the component. You can let me show here. This is basically en2. Okay, you can write e2n, and in the base, this is the normal component, and in the base it's basically the e2t, which is the tangential part. Okay, similarly we have to make for this also. Let's make resolve this and this. Similarly, this is the tangential, so e1t, and this one is basically e1n. Okay, now let's solve for the case of electric field. Okay, so how you can solve this? You can wrote the relationship basically, and that relationship is basically, you can say your is coming from 1. So basically this, uh, so it's basically coming from 1. So you can write first of all this field e1t, so e1t. Okay, and in the case of e1t, your length is basically the dl. You can write complete dl. Now it's going into, but in one medium it's half, and in second medium it's, you can see, again half in one medium and half in the second medium. So to because we are dealing first with the first medium, so for the first medium it becomes half of the dh. So again, uh, okay, you can now e1n, because okay, going your normal part e1n. Now your the direction is half in the first medium and it's dh, so it becomes dh over 2. Okay, similarly half in the second medium, so you can write it as here is basically the e2n. Okay, so it becomes e2n, normal part in the second medium, and it's half of the dh. Again it's dh divided by 2. Now it's this in the second medium, and it's basically in second medium, and it's basically the its base, and its base is basically already told e2t, so it becomes e2t, and now your length is basically dl, so it becomes dl. Okay, now you can see it's going in, you can see your electric field is going in this direction, and now your length is basically in opposite direction. Electric field is going in, and you can see now you're, after crossing, you're going into, so this is opposite direction. So for the case of opposite direction, now we have to write it now by minus, and again half of dh into the second medium, and for that, and for the downward is basically we have to use en2. Okay, so minus of en2 and half of the dh, so dh divided by 2. Again half of the dh in the first medium, and this is a case of e2t, so sorry, e1t. So you can see this e1t going into. Okay, so minus of e1t, again dh over 2. because you have to find the electric field, and we must have to concise our this length. How we can concise this length? If we remove the dh parts, this dh part and this dh, how we can remove the dh parts? Because we have to find the electric field on the surface, okay, on this surface, which I make it here, okay. To find the only on the surface, you must have to shrink this dh part. So how you can shrink? If your dh value is nearly equals to 0, so this is how we can shrink and we can find electric field on this path. So for that we must have to put our dh approximately equals to 0. So our equation, this equals to 0, this becomes equals to 0, this becomes equals to 0, and this becomes equals to 0. Only you will left with, and this is basically e1t, okay, minus e2t equals to 0, okay. What you conclude from this is basically your e1t is basically equals to e2t. So this is very important relation, and that relation basically describes that electric field is basically electric field, okay. Tangentials components are continuous basically because they those both are equal. So you can conclude that basically the electric field tangential component, you know, where are the tangential components? This is the tangential component, this is the tangential component of the first medium, in first medium, and this is the tangential component in the second medium. So you can conclude, because e1t is, now becomes equals to e2t, so tangential components of electric fields are now, and our results are equal. So we can conclude that electric field tangential components are continuous, okay. Electric field tangential components are continuous. Why continuous? Because we show the results, they are equal. Similarly, you can also write it as like this, because this direction and cross e1 minus e2, you can also write it as here. Similarly, you can find the same thing for the case of magnetic field. For the case of magnetic field, let me show you here. You have to resolve this equation, as we, for the case of electric field, we resolve this equation. For the case of magnetic field, what you have to do, you have to resolve this equation. You have to take the, again, complete integral over this dot dl, this must now becomes equals to 0. This is for the case of magnetic field, this is for the case of electric field which we drive. So this is your homework. You can find similar for the case of magnetic field. Let me show you some results. Your results are also same. Your h1t should be equals to h2t, as we derived here. Your e1t is equals to e2t. So you have to prove your magnetic field tangential components are continuous, similar which we find here, like electric field tangential components are continuous. So you must have to prove this, okay. Similar procedure, in this procedure again, this shrinks out and becomes equals to 0. So these factors becomes equals to, you only left with the same aspects, okay. Let me show you the original equation of this. This is for, in this case, basically this is the original equation, but for in this case we use this. In magnetic field we have to use this, but what's basically the original equation, which you don't have to use in this, but let me just show you that equation is basically this is basically your, okay, whole integral basically b dot dl, it's basically equals to, okay, your surface integral, okay, and now j plus partial d by partial t dA, okay. This is basically the official equation of this. So that's all for today's lecture. Okay, so basically there is a new thing for this, like that if you want to find your, in the case of magnetic field, if you find the magnetic tangential magnetic field components on the surface, okay, on the surface, not in space, on in the surface, what you have to do basically, you know that in this relation, this integral j dA, just this j is basically you know that current per unit area. Okay, this j is basically the current per unit area, which is the conduction current, and this is the displacement current. Okay, this is somewhere something other, but this is the conduction current, and this j is basically the current per unit area. To find the current on surface, so first of all we must have to convert our current per unit area into current per unit length. So how we can convert this j into length units? So let me just show you a bit here, like that is basically you know that this integral j dot dA, this is you know that basically the current per unit area, current per unit area. Okay, current per unit area. But if you want to find your current on the surface, so you must have to convert this per unit area into per unit length. So how you can convert, as it is j is as it is current per unit length, per unit area. So area, you know, the unit of area is meter square, and basically it's L dot L. So because we use L dot L, so we must have to multiply it by L dot L also. So cancel one L with one L, then you will only get with I dot L divided by L. Okay, and this I by L is basically equals to same integral as it is, and this basically equals to I by L is basically equals to K, and this L basically becomes DL. Okay, so now you can see here that this K is now basically the current per unit length. Okay, if you want to find current in per unit area, you have to use this relation. But if you want to find current onto the surface, then you have to use this, because this is the K is basically the current per unit length. If you are finding current per unit length for the case of magnetic field, then your final relation is basically equals to your H1T is basically you can say minus H2T is equals to K. Okay, in general case we know, we showed that E1T minus E2T equals to 0. Similarly, when you prove for this, you will get H1T minus H2T equals to 0. But in specific case which I showed you here, if you want to find your current per unit length, okay, in that case is K, which is the current per unit length, then in that case your H1T minus H2T equals to not equals to 0, it then equals to K. So that's all for today's lecture number 6 of advanced electromagnetic field and waves we discussed in this lecture. So thanks for watching. We will update more with you with more lectures of advanced electromagnetic field and theory and waves. Okay, so thanks for watching. Stay tuned with us. Allah Hafiz.